Hello, folks. For the past 2 months, I've been preparing several video segments on use of the Catia's native FEA solver for solving composite problems, analyzing composite parts. Now, all of these problems that I've been doing so far have had a very simple geometry, namely they were flat strips. So the next few that I'm going to be doing, the geometry is slightly more complicated, and but still they are not, something that is extremely uh, intensive in the surface. It's basically in this case it's a hollow drive shaft, and the next one that I'm going to be doing is going to be a cylindrical pressure vessel. So it's one notch more complicated than a flat surface, but if we cannot get the answers here, if we cannot do these problems, there is no hope in getting any meaningful things in uh, complicated geometry, such as maybe a airplane wing or a compressor blade, etc. Okay, so let me start with this thing in the see now in slideshow mode. We're going to be doing a hollow tube, which is under the torsion, and this hollow tube is made of a two layers of carbon epoxy, which are at 45 and minus 45 with respect to some rosette. Okay. Now the information, geometric information here is diameter 6 inches, a length of 20 inches, and the applied torque is 75,000 pounds. Now these are large loads for a geometry like that with particular thicknesses that you see down here. However, we're not interested in that aspect of it. We just want to make sure how to model a problem like that and get the stresses and everything. The issue of failure is something that we're not going to be addressing in this particular problem. Now, the 45 and minus 45 degrees have those layers of 0.1 inch thick. Okay. Incidentally, uh, all the videos that I've done so far on composites were done on V56 R2016, but today my license at the university was not working, so I'm going to be doing it with R21 with minor changes, if any. It runs on other releases. The modeling strategy is as follows. It's a very simple problem. It's a hollow tube, right? So basically, we have a cylinder which is hollow or hollow, not capped at the ends. But what I'm going to do, this problem, I'm going to do it, uh, take this cylindrical surface and basically make two surfaces out of it, the top surface and the bottom surface, okay? And for each one of them, I'm going to create a rosette. For the top one, I'm going to create a rosette just like you see up there on the right corner. And for the bottom one, a rosette down below. Now, you might say, well, can we not do it for a single cylinder without splitting it up into two? Well, it is going to be problematic. I'm not saying it's not possible, but it's going to involve a lot of work. And in some other software, such as ANSYS and Abacus, this can be done without any difficulty, but I could not get it to work, in a reasonable length of time with uh, a single surface. Okay. Now, the reason is you're going to have a hard time when you try with a single surface is that you will notice that for a particular lamina, which is supposed to be 45 degrees, although it's saying it's 45 degrees, all of them, but when it comes to, there's a seam here, there seems to have been a seam, which suddenly this angle changes. And with care taken, this can be fixed. This issue can be fixed in the case of two top and bottom surfaces, but with a single surface, this issue arises and it has to be fixed, and this is not acceptable. So basically, we want these composite angles to be like that, and this can easily be done with if you have two two surfaces, and not so if you have a single cylindrical surface. Now, and I want to go to the CATIA documentation, which actually raises this issue. This is from online documentation. It said for U-shaped and recovering surfaces. So this actually, that's surface that we have, the full cylinder, on the side of it, if you look at it, it's basically the shape of a U. Okay, so it seems that they're saying this is what you need to do, but didn't work. So maybe I didn't understand this, or I was not doing it right, but I leave it to you to work it out yourself. Now, we're going to be comparing the calculations with something that we already know, the analytical calculation. So if you go back to this, if you go to this source, which is a series of lectures developed at East Carolina University. This problem is solved for you analytically, plus 45 minus 45 on a cylindrical surface is solved for you analytically, subject to assuming that the material properties are these. Okay, so these are the material properties. I'm going to be using it. I'm not worried about failure, so don't worry about the strength properties on the right. Now, if you apply a 75,000 pound inch-pound uh, torque, for the 45 degree ply, we should be getting 1 mesostress of this. Same thing for the minus 45. And the stresses are kind of the same, except that the signs change, okay? So the one thing that we're going to see is that there is there is a point that one has to keep in mind when you look at the stress distribution. These numbers we can generate. These are coming from hand calculation from that source. These you can get it, except that CATIA call them stress component in the global direction. This is a bad terminology because these are fiber direction and transverse. And CATIA calls them, if you want to match these, you have to plot the stress components. Now, one mesostress matches, there is no problem. But this issue of components of stress in CATIA's FEA is not very well documented, and one has to be a bit careful. Finally, I said that this is done on R21, and therefore you got to be careful. Okay, so I'll keep this thing handy because I go back and forth between them. The first thing I need to do is to create two material, because material properties for this carbon epoxy that's not in the database. So first we're going to create them, and I'm going to let's go here. Let me start CATIA. Yeah, I'm going to create. They are the same for the uh, or they have the same. Yeah, 45 degree ply and minus 45 degree ply have the same thickness, so that's not an issue. Okay, just give it a minute. All right, let me kill this. The first thing we're going to do is to create our material property database. So we go to Start, Infrastructure. I've done this thing several times on other videos, but if it's the first time you're watching it, it may help. Material Library. This is my own material library that I'm going to create. First of all, this thing, I'm going to give it a, let me double click on it. And first of all, the name of it, I'm going to call this thing drive shaft. Drive shaft. Okay. Apply. So notice that the name changes here. And then you go to composite. It's a unidirectional ply, unidirectional fiber or lamina. And the cured thickness is 0.05. I don't have to worry about the other ones, the other properties. Notice, I'm sorry, but let me check this thing again. What was that? 0.1, 0.1, not 0.05, 0.1. So cured thickness 0.1 inch. Apply, and then analysis. We are doing orthotopic material 2D. So we start putting those numbers. The longitudinal Young's modulus was 20 million, 20 e to the 6. The transfers was 1.2 millions to the 6, 1.2. Try it again. 1.2. Excuse me. E to the 6. Poisson ratio 0.25. Shear modulus in the xy plane was 0.8 e to the 6, 800,000, and these are half of that, so 0.4 to the 6 and 0.4 e to the 6. Right? Okay. This family name, if you want to change it, you can do that, but I'll leave it like this. Actually, let me go ahead and change this. New family name, I call it my family name, my family. My composite family, my family. Okay. All right. Now I'm going to save this. Okay. By the way, if you want to create other ones, you click on this ball and then you can create it. But we don't need it. So I'm going to say file, save as, desktop. I created a folder called drive shaft December 19, and the name of it is my database. Okay, so far I haven't done anything new. We did this thing before. I'm going to close this, and in fact, if you go to the desktop and check the drive shaft folder where everything is going to go, here's the database that I'm going to be using. Okay, not the default database of Catia. Okay, so now let's go and start with the part. So let's start with the part file. I'll call it drive shaft. Drive shaft. Immediately, I'm going to save this thing. File, save management, save as. On the desktop, that folder, which was right here, drive shaft is the name of the part, and I'm going to save this. Okay. So we're going to go to generative shape design to create a geometry. We go there. And I'm going to systematically create these top and bottom surfaces, okay? You may want to skip some steps if you feel comfortable, but I'm going to do it systematically. So here on the YZ plane, I'm going to sketch a semicircle with a center here, center, and this is going to be eventually the top one, okay? And let me give it a radius. A radius was, I believe, 3. Okay, if you look at our information here, the diameter was 6, radius is 3. Okay, and then exit, and I'm going to extrude it, extrude in both direction, mirror extent, and I'm going to make it 10 inches long because the total length is 20 inches, so 10 inches in each direction. Okay, so here's the situation. I have sketch, I have extrude. Now, I am going to join this, and the reason I join it, although you can go ahead and do the problem without joining, but in the previous videos I said if you join it, that will give you a direction to the surface, and the opposite to that direction is going to the direction of the normal to the shell elements. Okay, so this way you have a control. So I'm going to join this there, and we say okay. If you double click on it, notice that it gives you that arrow. That means that the elements that you shell elements that you use to cover this surface, their normal is opposite to this, and I don't like that. I want it to go in the other direction, and that'll do it. So if you double click on it now, you see that it's pointing down. Okay, this has nothing to do, by the way, with the direction of draping and things like that. Okay, the next thing I want to do, I want to extract the boundary of this. Now, boundary extraction is, you are probably familiar with this. It's here, it says right there, boundary, okay? And you select that join, and the boundary is selected. Now, to make my job easier, what I'm going to do is I'm going to call all of these things for the top, because it's the top piece that I'm going to do. It's a bookkeeping, which makes it easier for us to keep track of what we're doing here. Properties, these are all top. One more, properties, top, and boundary top. Uh, Properties top, top. Okay. Incidentally, while I am here, well, actually, let's go ahead and do the bottom one. How about that? Yeah. So on the same plane, on the YZ plane, I will sketch another half a circle. Make that radius 3. Exit. Extrude it. There's the extrude right there. Same information, 20 inches in each direction. And then we're going to join it, the bottom piece. And notice that when you double click on it, the cancel. If you double click on join, the arrow is pointing down, so we're going to flip it up. I'm going to extract the boundary of this, the boundary of that. So these are exactly the same steps that I did, except that it's for the bottom piece. So boundary is right there. Boundary of join is down here. You say OK, and I'm going to systematically change all of these to the bottom. Properties bottom. Properties bottom. Bottom. This is what I said. You can skip some of these steps if you can remember what you did. Properties bottom. Okay. Now, I'm going to create my rosettes, my coordinate system. So I showed you this configuration. So for the top one, Z up, X along, and Y, of course, coming towards you. Yep. So this is the axis system right there. Origin 0, 0, 0. Okay. So let me uncheck this current, by the way. So there we are. You can see that Z is going up, Y X is along the cylinder, and we are good. This is the axis system. I'm going to call this thing top. Properties. This is for the top piece eventually. Let me do another one. Coordinate system. This one is the same origin, and by default, it's going to put it exactly on top of the other one, but I want this thing to be rotated so that Z is pointing down and X is going in the other direction. So I'm going to rotate about the Y-axis by 180 degrees. So you put the cursor there, right-click, rotate 180 degrees or minus 180 degrees. It really doesn't matter, but I'll make it 180. Doesn't matter. Okay, so if you look at this thing carefully, for the bottom one, X is going in this direction, in the negative global direction. Z is pointing down, and Y is going into the screen. Okay, so I'm going to call this thing bottom. Properties, bottom. Before we forget these things, let's save everything. Save. Now, the rosette that I'm going to be using, I have a choice later on to do it as a Cartesian rosette or a cylindrical rosette. For this particular problem, it doesn't matter. for for a simple reason that the geometry, the loading is actually, if you look at this little patch, the loading is in this plane. It really doesn't matter. So I can use Cartesian later on, or cylindrical, but I will uh, leave it like this for now. Okay, leave it like this for now. Okay, so where are we? This is all done now. Uh, I will create two points, one at this end, the other at that end. Look, it makes it easier if I applied my load. You can apply the load by, for example, fixing that end edge later on, clamping it, and applying a torque to this front edge. But you can do that. But I suggest that we use virtual part so that the point of application of uh, that moment or that torque is not directly on these, but it's at a different point, but it's going to transfer it. If you do not understand this, it's okay. Just go on later on, clamp the ends and apply the moment on these edges. Okay, but you learn something new here. So I'm going to create 2 points here right now. A point there, which is this was 10. Remember, this half of this was 10 inches. So I'm going to put it at location 1 4 preview. So it's right there. You can see that. And this is going to be front, just so that I can see what's going on. Front. Another point. Where's the other point? Right there. This is minus 14 at the other side. Oh, maybe I didn't do it. What did I do? Minus 14. Did I do that? Oh, cancel. The reason that it ended up at some other location is that double click on the button. Okay, so that's good. So this point 2, where is it? Uh, Minus 14. Preview. Let me see, cancel that. I'm having a problem getting this other point there. This one is right there. We can see that, there's no problem. Okay. This other point, uh, oh, minus, let's see now. So let me make this thing minus 20. Oh, it's right there. Yep, yep. So minus 24. How about that? Right there. Minus minus 30. That's too much. Minus 28. Hey, listen, I want a point on the other side. Do it any way you want. Okay, that's good. That's good. Okay, right there. I don't know what was going on here. So let me call this thing the back. Properties back. Okay, good. So we are done here. Let me save everything. We are now going to go and create our composite plies. So we go to switch to composite design, mechanical design, go all the way down, get a composite design, right there. So we are in the composite design workbench, okay? And you create the parameters. You click on this, composite parameters, add material. Remember, I created my own database. So I go there on the desktop. In this folder, I created a material database. And we say, okay. Notice that it picked up the one, there's only one one thing in it and it picked it up right there. Remember the cured thickness was 0.1? Okay. And the angles that we have is 45 and minus 45, which is already in there. We don't have to worry about it. Okay, very good. Okay. Now we're going to start our plies. Okay, and I'm going to do it the long way. In other words, manual ply creation. Okay, so here is the ply group right there. See that? Ply group, ply group. The name of it I'm going to call top. First I'll do the top one. The surface is that surface that I created on the top. Draping direction, I want it in the upward direction. Although I'm going to symmetrically place it about the surface, so it really doesn't matter, but I'm going to flip it up. Okay. And notice that you have a choice between Cartesian and cylindrical. If you do cylindrical, which it could be that it makes more sense here, it's going to ask you for a neutral fiber, okay, neutral fiber direction. You can do the problem with a Cartesian one, nothing is going to happen, this is going to work very well, but the pressure vessel that I'm going to do, definitely cylindrical will be better. Right now, we're going to use Cartesian, and if there's time, I'll come back and change this thing to cylindrical, and we'll see how it works there. But it doesn't matter. Right now, we're going to leave it. And rosette. Now the rosette. Remember, we have two of them. One of them was the top one. The other one was the bottom one. We're doing the top surface, so I select the top rosette and lock the plies draping direction. Lock it. So this was they're all going to be draped in this direction. Okay. So we created the ply group 1, which is called the top. I have to do this thing for the second one too, but might as well do that. So you click on this. This is the bottom, BOT. For the surface is the bottom surface. Rosette is the bottom rosette. Okay, and again use Cartesian, unlock the directions. By the way, make sure it also goes down, draping direction downward. So I flipped it. Okay, good. So we have two ply groups here, but no plies yet. Now we can go and create our plies. So let's do this. It's going to ask you for, okay, which ply group you want to put it in. We are doing the top one first, so I put it in the top one. Okay, it says, what is the contour? So I click on this add, or click on it. And then I'm going to select that boundary, which was called, remember I got the boundary for the top one, so I select the top boundary and say OK. And then we're going to go to the attributes. Material is the drive shaft, and it's 45 degrees, okay? And notice that automatically picked up the rosette from the ply group. Say OK. Now the second one, we're going to click it again on the ply. Goes in the top. Boundary is still the same, top boundary. And for attribute, it's going to be minus 45. Remember, if you have many of these plies, then this is going to become a laborious process. You can use all these tricks that I talked about in the earlier videos. You can do it by zone method. You can do it by copy and pasting plies, etc. But there's only four of these that we have to do, 2 here and 2 on the next one. So I decided to do that manually. Okay, so where's the other one? Now another ply, but this one is going to go to the bottom group. Okay, a boundary is going to make sure you select the bottom boundary. For the other one was top boundary. And attribute material is correct, and then this is going to be 45 degrees. One more, which is the last one. Bottom. The boundary is still this bottom. And for the ply, direction minus 45. Okay. I think we have done everything that we needed. Save everything. Good. So now we're going to go to generative structure analysis, or actually I'm going to do the advanced meshing tool because I want to create a nice fancy mesh for you. If you are happy with triangular mesh, you can go and do it all at the same time in the generative structure analysis. Let me change my rendering here. Okay, good. So let's do the top one. So here is the surface mesher on the top, and I'm going to put the 0.5 as the size of the element. We may have to come back and make this thing bigger or smaller depending on how things are parabolic and quad only. And then zap it. Zap it means, okay, mesh it. Oops, not here. Where is it? Oh, right there. Let me move this thing out. There. Zap it, mesh it. It looks like that. So that 0.5 was fine. And then exit. Okay. Now do the bottom one. Again, you click on it. Do the bottom. Same parameters. Zap it. Okay. And exit. Okay. Notice that if you had a single surface, and it was, a single surface, it would do it all at the same time for you. And this is why, well, things get kind of messy. So over here, I'm going to make these name changes. So this is the top one, again for bookkeeping purposes. Top, properties, bottom. Okay, we are done here. So let's save our analysis. File, save management. Here is an analysis file. We save as in that same folder that I created. I'll call it analysis 1. Okay, fine. And we save everything. Then we're going to go to generative structure analysis. Okay, first thing I'm going to do is I import the properties. I import the properties here. So let's go ahead and do the 2D property right there. Right there, not this one. This is for a regular mesh, not a composite mesh. That guy, imported composite property. What it's saying is that, okay, where is the support? The support is the top one. We're doing the top one first. And where is the ply? Where are the ply? We're going to do it by plies. So we have to go and select the group one, ply group one, which was called top, from here. Okay? We have to go to this, expand this thing, basically go back to the part. And we're going to place it symmetrically above the surface. In other words, one of these 0.5 degrees is going to be below the surface, minus 0.5 is going to be above the surface. That's what symmetry means. Okay, say okay. By the way, this is the top one that I did, so I might as well change the name now. These are all bookkeeping, they are not necessary. Let's do the other one. So import for the bottom surface, plies. Now the ply is going to be the bottom ply group. Say okay and okay. I'm going to change this thing to name of it to bottom, BOT. Okay, so the only thing that I have to do is to apply the restraints and the torque and everything. Okay, so first thing I'm going to do, I'm going to hide. I put the cursor here. Hide the plies, stacking basically sequence. Hide it. And I'm going to hide also the boundaries. Where are the boundaries here? This boundary I'm going to hide, and this boundary I'm going to hide. Top and the bottom I'm going to hide. Because now I have access to these edges. See that? Okay, good. So I'm going to create two virtual parts. Listen, if you don't want to do it like that, no problem. You can clamp this end and you can apply torque to these. But I'm going to apply it with a virtual part. So I go here. I'll use a rigid virtual part, right here, rigid virtual part. Okay. So it says, what is the support? Well, let's start with this guy. This is the top one. And the handler point is right there. And then another one, the bottom edge. And the support is that. Okay. If you're interested, these things that you create, you can go and rename them. So, for example, top, upper circle, or you can call this thing front, upper, front, lower. Or let me do that actually. Let me do that. So properties. This is going to be front, top. How about that? Front, top. I'm going to change this thing to front, bottom, front, bottom, all bookkeeping. Front, bottom, There we are. And I go do exactly the same thing in the back. So which rigid virtual part, support top, handle point right there. If you don't use if you don't create a point here, the handle point is going to be automatically at the centroid of that, so it's going to be on that surface, which is okay. There's no problem. In fact, I can change the name here too. So it's going to be back, top, and the last one, handle point right there, and it's going to be back, bottom, back, bottom. Okay, so let's see now. Very good. Oops, I thought I changed it here. Maybe properties. This was, I don't know, somehow didn't change the name. Front, top. Oh no, sorry, back, top, back, top. Yeah, properties, back, bottom. I need a K there. Okay, save everything. Okay, so we're going to clamp that back side. So here's the clamp icon. Where's the clamp icon? Right there. I'm going to put it on the virtual parts. Now notice that I can select the virtual part from the screen right there. But when it comes to picking it from the tree, oh yeah, you have to pick it from here. Let me do that. I didn't like that, so I'm going to change this thing to. I thought that when you change these things, it also changes it here. It doesn't. So let me change this thing to front, top. I could have left it the way it was. Front, bottom. Properties, front, bottom. Front, bottom. Okay, good, good. So clamp. I'm going to clamp the back side, back top, and I don't think you can do it. You have to do it one at a time, because if I select this one, it just selects just one. We won't do two of them. So cancel that. Let's try it again. So we do the back top, and again back bottom. Okay, now we apply a moment here, and that moment obviously has to be half of it to the top, half of it to the bottom. So moment is over here, or the torque is over here. You go under distributed force, moment. On the top one, okay, so this is going to be about the x-axis, so it's going to be uh, 37500 lbf times in. It's going to convert it to Newton meter because my units are like that, but that's okay. So, and then again, another one to the bottom piece, same numbers because I already converted it in the same direction. Let me change my units here. Tools, options, for moment, force moment. Where is the moment? Moment. We're going to change that thing to pound inch. Okay, now if I check these loads, it's going to be in the appropriate units. 37500. Okay, now, oh, you know what? Actually, this is fine, but there is an alternative that I want to show you. What I could have done is I could have applied a moment in the opposite direction to this end, but then this problem becomes static. It becomes free to move as a rigid body, which then you have to use the 1, 2, 3 rule, or you have to use the isostatic constraint. I'll leave it like this. Okay, I was planning to do it with the isostatic constraint, but since I told you I was going to clamp this in, we leave it the way it is. Okay. I think we have done everything. So save everything. Before running this thing, I want to see and make sure that the direction of my fibers on the two sides are like that. Okay, so let's go ahead and do that. Now, how do we check that thing out? We go to the uh, uh, in order to check that, first of all, you have to run it, but you don't have to run it for results. You have to, for analysis, you can just ask for it to do the mesh, because in order to see those direction, you need basically the mesh. You don't have to run the problem. Done. Okay. So you put the cursor on properties right there. See that? Put the cursor on properties, right click, generate image, composite angle symbol. You say okay, and we then look at it. Now, let's bring this thing from hiding, show this thing, because it's easier to see what's going on. Right there. You see this? These arrows, the direction of the arrows don't matter, but these lines have to be lined up. They cannot be one like this and one like that. Okay? So this is gonna be fine. All right. So save everything, and now we're gonna run it, but not only the mesh, but we're gonna do all. Basically, give me the numbers. All right, first look at the deformation. You click on this, or displacement. Okay, very good. So let me change the rendering here. Average ISO, and change the rendering to material shading. Looks like that. Now, if you don't want to see the virtual part things, so I'm going to double click on this thing and say, don't show me the virtual parts, don't show me everything, just show me the mesh, uh, which was uh, what was it? Oh, bottom and top. Yeah, and top. Remember, I changed the name of the mesh to bottom and top. Okay, so this is torquing. Very good. Then I'm going to look at I want to look at the von Mises stress in different plies. So we go here, we put the cursor on your static case solution. Put the cursor on this line, right click, generate image, and let's filter it with according to stress, so that only the stress stuff is shown. And then stress at the element level or node level. Let's try the node level. Good. You might say, okay, well, why does it look like that? Well, first of all, this is not von Mises stress. This is not. Double click on it. On the visual, we want von Mises stress right here. These were stress component that we are looking at. Okay, good. Now, you might say, well, wait a minute, isn't it supposed to be constant? Well, look at the number first of all. The red is here, away from the support. So what we can do is this. Double click on this. First of all, show me the discontinuous ISO. Oh, that's a lot better. Discontinuous. And don't average things out, because things are crazy down here. So don't average it out. Man, what is the number here? Just put the cursor on it. 1.29 e to the 4. The other way that we can fix this, first of all, double click on this. Say, don't show it to me on the deformed shape, show it on the undeformed. But let's create a box group. There's the box group. In other words, show me all the stuff in this box away from the ends, basically. Now you can resize the box by clicking on that and moving it around and resizing it, translating it right there. Show me only the stresses, von Mises stress, in this box. So double click on that. Sorry, double click. Let me hide the box first. Put the cursor there. Right click, hide it, and double click on this. For selection, don't show me everything, just show me the box group there. And guess what? Look at the number, 129. Okay, don't let these things fool you. This is all numerical round off error. 129. Look at what the theory is supposed to give you. 129 10 to the 4. Now, for both plies, so this was actually, double click on it, this more, this is for ply number 1. If you go to ply number 2, it's going to be the same numbers. Very close to it at least. Okay. Now, the reason that there may be some differences here is because these plies are relatively thick. Okay. Point 1 is thick, but if these were thinner plies, these would be very close to each other. Okay. Now, this was 1 Mises, right? Yes, this is 1 Mises stress. Now, let's look at the stresses in these fibers. That is where the problem comes in. I would have liked to see some other way of naming these things, but it's going to be global direction. So let's go here. Let me say, okay, this is for 1 Mises. Let's do another one. Put the cursor there, right click. We could have done it in that one too. And filter it with the stress. Select the nodal elements, nodals. Okay, just show me the stuff in the box group. So double click on this box group. Okay, but these are the numbers. Well, what are these numbers? What are these stresses? These are in the local direction. Let's change this thing to global direction and C11. In other words, component sigma 1. Okay, which ply is it? Ply number 1 and 564, etc. Now, what did we have here? We have 579. The only thing is that the order of these is also sometimes reversed. This is why, unfortunately, these are not well documented in the program. But if you go to C22, 1.26 e to the 4, 1.26 e to the 4. Okay. The second one was C11 is, so these things are reversed. Now, it's unfortunate. Now let's check this with C12. 0. Well, it's not 0. Yeah, but it's 26. But 26 compared to what? 12,000. So effectively, these are zeros for the shear. That's these things. Effectively, these are zeros. Okay. The other thing is that we can go to laminar number 2. These numbers are going to be very close. Again, only the sign will change. So 595, supposed to be here. Don't let it bother you. These numbers are also can be changing because of the way they wrote the code. So the von Mises stress doesn't depend on that. It doesn't depend on these. The signs don't matter. Von Mises is always positive, but you've got to be careful in when it comes to interpreting. This is 1.28. 1.28. These are theoretically supposed to be the same, assuming that assuming that based on theory. But here, of course, these are numerical, but they are closer. And C12 again pretty much 0, okay, compared to 12,000. Okay, so I think I've said everything about this this torque under uh, well, drive shaft under torsion. The only thing that I didn't do is change the, we have the time to do that, so let's go ahead and actually redo this calculation. All we have to do is to change the type of coordinate system that we use. So I'm going to click on the top. Okay, see, it says you want to use the cylindrical coordinates. If I say yes, then it's going to ask for neutral fiber. Neutral fiber basically is going to be the axis of this. So let me cancel that. I'm going to go back to part design. Okay, we're going to go to part design, generative shape design. If you look at this icon, let me grab these, bring them out. Uh, this right there. You see that? Change that to expand the toolbar, you're going to go Access, and it says what is the element. So you select one, either the top or the bottom system. It creates this axis for you. You can see that if I turn it, kind of hard to see it here, but there is an axis there. You can see that. Say OK. So let's go back to our composites. Okay, select cylindrical. For the neutral fiber, select that axis, and then the same thing for the other ply group. Cylindrical, select the neutral axis, and let's go ahead and run it. Let's go run it. And look at the stuff first of all. Our translation, I'm sure it doesn't make any difference here. You can see that. Even if you look at the numbers, you can check, deactivate. Let's look at the one meso stress. Activate. 1.31. This was ply number 2. Remember, ply number 2. This was ply number 2. Ply number 2. If you go to ply number 1, it's going to be 129. So it didn't make any difference in this particular problem. Let's check our deactivate that and activate this guy. Let's check what this thing was. This was C12. Yeah. So oops. You can see that in this particular problem, it made absolutely no difference. But it will make a difference when we do the pressure vessel later on. All right, folks, have fun.